Good evening, ladies and gentlemen. The subject of my lecture is electrolysis and related processes for materials manufacturing and conversion, electrochemical materials, electrode materials for fuel cells, batteries, and electrolysis. If you want to talk about various batteries, fuel cells, and electrolysis processes, we have to recall some basic concepts and definitions concerning electrochemistry. First of all, a strip of metal used in electrochemical studies is called an electrode. The electrode immersed in a solution containing cations of this metal is called a half cell. Electrode potential is a measure of the electric charge density on the electrode at which an oxidation-reduction equilibrium has been established in half reaction, such as that reaction presented here. If we properly connect appropriate two half cells, we will obtain an voltaic cell. Let's say a voltaic cell. Both the metal electrodes and the electrolyte solution have to be connected. The electrodes are connected through the metal wire to provide the flow of electrons. The connection between the solution is called a salt bridge. The ends of the salt bridge are plugged with a porous material that permits ions to migrate through it, but prevents the bulk flow of the liquid. As a result of the connection, we will obtain a voltaic cell, which is characterized by the electromotive force. And the electromotive force for this voltaic cell is equal to 1.1 volt. According to galvanic series, I presented here the section of the galvanic series, very shortened, and according to it, the standard potential of zinc electrode is equal to minus 76 volt. And the standard potential of copper electrode equals to plus 0.34 electrode, and the potential of the cell is potential difference between the two half cells. It can be confirmed by the voltmeter indication shortly afterward the connection. Of course, as the reaction proceeded, the potential diminishes. If we connect zinc half cell with a copper half cell, the changes will occur. Zinc atoms lose electrons at the zinc electrode anode and get into the solution as zinc 2 plus cations. The electrons from zinc electrode are transferred through the wire to the cathode, where they are captured by copper 2 plus cations from the cathode solution, which deposit as a metal on the cathode. Accompanying nitrate anions migrate through the salt bridge to the zinc half cell to neutralize the excess of positive charge of that zinc 2 plus. and in turn cations, potassium cations migrate in the opposite direction through the south bridge to the copper half cell to neutralize an excess of nitrate anions. The oxidation process is represented by the first reaction. The reduction process is represented by the second one. I also presented here the next reaction and the cell diagram. The anode is an electrode at which oxidation occurs, and the cathode is the electrode at which reduction occurs. This electrode is placed usually at the right side of the diagram. In this type of cell, in voltaic cell, the electricity is produced as a result of this spontaneous reaction. Let us consider the electrochemical cell called the electrolytic cell, in which electricity is used to produce a non-spontaneous chemical change, the reverse of spontaneous reaction. Let us suppose the same cell is connected to an external electric source of voltage greater than 1.1 volt, as it is shown here in the picture. The electrons are forced into zinc electrode cathode and removed from the copper anode. The net reaction in this case is the reverse of the voltaic cell reaction. The mass of zinc cathode increases during this process, whereas that of copper anode decreases. So the electrolytic cell works in this way. However, if you want to predict the electrolysis products, we have to take into account of a potential, which is necessary to cause a particular electrode reaction to occur. Exemplary of a potential for hydrogen discharge at a platinum electrode is practically zero, but at the mercury electrode it reaches about 1.5 volt. The nature of the electrodes is important when predicting electrolysis. The inert electrodes are desirable. The platinum inert electrode provides the surface area on which an electrolytic half reaction occurs, but it doesn't take part in them itself. Moreover, competing reactions may occur in the solutions. In the electrolysis of aqueous sodium chloride using inert electrodes, two oxidations and two reduction half reaction must be considered. The potential, as we can see from the picture, the potential for the oxidation of the second half reaction is less negative as compared to that of the first reaction, and oxygen may be expected at the anode. On the other hand, oxygen revealed height of a potential as compared to chlorine. And in fact, in the industrial electrolysis of concentrated aqueous sodium chloride, the chlorine contains less than 1% of oxygen. I'm talking about electrolysis of 5.5 molar aqueous solution of sodium chloride. And however, oxygen is more important product in the electrolysis of very dilute sodium chloride. The first oxidation reaction, I mean oxidation of chloride to chlorine, and the first reduction reaction, reduction of sodium cations to metal sodium, solely occur in molten salt only. The electrolysis of sodium chloride on the industrial scale is called chloralkali process, named after the two principal products, chlorine and sodium hydroxide. In the diaphragm cell, this is the diaphragm, chlorine is produced in the anode compartment, and hydrogen and sodium hydroxide are produced in the cathode one. The purpose of the diaphragm is to prevent contact of chlorine with sodium hydroxide, otherwise chlorine disproportionates into hypochlorite, chloride in chlorate. And the level of sodium chloride electrolyte solution is deliberately kept higher. It enables gradual flow of sodium chloride between tanks and reduces a backflow of sodium hydroxide into the anode compartment. And the final concentration of sodium hydroxide in the cathode compartment is about 50%, with up to 1% of sodium chloride. The anode in this process is made of graphite or titanium. Higher purity sodium hydroxide is obtained when electrolysis is carried out in a mercury cell. The cathode is the layer of mercury that flows along the bottom of the tank. Anodes are situated above in the sodium chloride solution. Sodium formed at the cathode dissolves in mercury. The sodium amalgam is removed from the cell and treated with water. Sodium hydroxide and hydrogen are formed. And this is the overall reaction I'm talking about. And the mercury cell requires higher voltage. This is 4.5 volt. Then diaphragm cell, the voltage of which is equal to 3.5 volt only, and consumes more electric energy. This is about 3,400 kilowatt hour per ton of chlorine, compared with 2,500 in diaphragm cell. The serious disadvantage of this cell is mercury, which has a very negative impact on the environment. The better solution is simultaneous increasing of the efficiency of the cell and use no mercury. A porous diaphragm was replaced by cation exchange membrane made of fluorocarbon polymer. The membrane allows hydrated cations passage, sodium plus sodium cations and um, uh, hydronium cations between cathode and anode compartments and restricts the backflow of chloride and hydroxide ions. Perfluorosulfonic acid, PFSA, polymer is the most commonly used material for membranes for fuel cells. Due to the high electronegativity of the fluorine atom, they have a strong carbon fluorine bond. The PFSA membranes that are relevant to fuel cells operation are highly stable against strong bases, strong oxidizing and reducing acids, hydrogen, oxygen at temperatures up to 125 degrees C. And they are also mechanically strong and can be performed in thin non-porous films of thickness as low as 25 micrometers. They are also highly acidic with highly conductive, especially when wet, and highly stable in operation. In selected tests, their lifetimes were exhibited over 50,000 hours. Their thermal stability, chemical inertness, and enhanced acidity of the sulfonic acid groups had the membranes make the membranes, their thermal stability, chemical inertness, and acidity of sulfonic acid group made the membranes originally developed for the chloralkali industry, but to achieve high power densities in fuel cells, much thinner membranes were developed. The PFSA consists of two regions. First, PTFE backbone, and the second one, side chains of vinyl ethers, presented here, which terminate in sulfonic acid group in a cluster region. The ionomer membranes function well as ion conducting materials because the sulfonate group form into clusters which are very hydrophilic and attract water. When the membranes become hydrated, the protons become highly mobile in the hydrophilic region, formed by the sulfonic acid clustering. These clusters effectively form channels through which hydrogen cations can move quite freely under a potential gradient. Now, batteries. Battery is a device that stores chemical energy for later release as electricity. The main difference between rechargeable and non-rechargeable batteries is that rechargeable can be put to use again after having fully discharged, while non-rechargeable ones cannot be charged again once they discharge fully. The battery consists of two electrodes called a cathode and anode in the electrolyte if a battery consists of a single voltaic cell, as in a flashlight, for example. When the electrodes are connected, chemical reactions take place at the electrodes, and electrons flow from the anode to the cathode. And sometimes some cells are joined in series, plus to minus, to increase the overall voltage of the battery. The automobile battery can be example here. If the reactions are irreversible, the battery cannot be charged again. This type of battery is called a primary battery. In contrast, the secondary batteries are rechargeable because the chemical reactions that proceed in the battery are reversible. The flow batteries convert chemical energy into electrical energy by a chemical reaction. Examples of primary batteries are as follows. Alkaline batteries, Leclanche dry cell, for example, in flashlight battery, silver batteries, and so on. So, let's talk about alkaline batteries. We can see a longitudinal section through an alkaline battery in the picture. Zinc anode reacts with the hydroxide ions, released from the cathode, producing zinc oxide and water. And electrons are released in this process. The released electrons combined with manganese 4 oxide and water to produce manganese 3 oxide and hydroxide anions. This is an example of non-rechargeable batteries, and these reactions take place in the above direction. Once all the manganese 4 oxide has been converted into manganese 3 oxide, the reactions stop and the battery no longer produces an electric current. Another example, silver oxide battery. It's a good example of primary cell. It uses silver oxide as the cathode material and zinc for the anode. They are available in small size as bottom cells, and the amount of silver used is minimal and not much expensive. Uh, uh, it is not much expensive contributor to the overall product cost as it could be suspected. The cell diagram uh, for silver zinc cell is presented on the right. The half reactions on this chart are as follows, and net reaction is presented here. As we can see, no solution species is involved in the net reaction, and because of that, the quantity of the electrolyte is very small, and electrodes are close together. This type of batteries, the batteries of this type are widely used in watches, hearing aids, cameras, and so on. The great advantage of these batteries is their high energy to weight ratio. Its storage capacity is 6 times greater than that of a lead-acid battery of the same size. Silver oxide primary batteries account for 30% of all primary battery sales in Japan, and these are data from February 2020. Specific energy of this battery is 130 watt hour per kilogram, and energy density of 500 watt hour per liter. They are characterized with high time durability and energy to consumer price seems to be efficiently low, and its nominal cell voltage is 1.55 volt. A good example of air battery is aluminum air battery. This is a kind of flow battery because it uses oxygen from the air, which is known as an air battery. The material that is oxidized is typically metal. It can be zinc, aluminum. In the aluminum air battery, oxidation occurs at an aluminum anode and reduction at a carbon air cathode. The sodium hydroxide plays the role of electrolyte circulated through the battery. The simplified representation of an aluminum air battery is shown in the picture. The half reactions and the net reactions are as follows. Because of the fact the concentration of hydroxide anions is high, aluminium 3 plus produced at the anode forms hydroxy complexes. The hydroxyl complexes. The battery is kept charged by feeding chunks of aluminium and water into it, and this battery can power an automobile even several 100 miles. Now some example of fuel cells. Fuel cells enables converting the chemical energy of fuels directly to electricity. The fundamental process in fuel cells is fuel plus oxygen to give oxidation products. The reaction that proceed in natural gas methane fuel cell are as follows. A fuel cell reaction is often rated in terms of the efficiency value E, which is equal to the ratio of delta G and delta H. For the methane fuel cell, E is equal to 0.92, and it is quite good result because the higher the E, the better the efficiency. The fuel cells based on the oxidation of hydrocarbons haven't been commercialized yet because of technical difficulties. The better solution is to use hydrogen in hydrogen-oxygen fuel cell. In this cell, the reaction of hydrogen and oxygen in an alkali electrolyte, this alkali electrolyte usually is 25% potassium hydroxide, produces valuable reaction of hydrogen and oxygen in highly alkaline solution, produces a valuable product, water. And as long as fuel and oxygen are available, the cell will produce electricity. The fuel produces the electricity. The fuel cell is neither, we can say, it's neither characterized with by limited capacity of a primary battery, nor does it have the storage capacity of a secondary battery. It's rather an energy converter. The cell based on hydrogen oxidation reactions presented here have been the most successful as energy source in space vehicles. And now let's skip to secondary cells. The most common secondary battery is the automobile storage lead-acid battery. This type of battery is used since 1915. This storage cell consists of a lead-negative electrode, anode during the discharge process, and a positive electrode which is made of lead-4 oxide, and this electrode plays a role of cathode during discharge process. They are immersed in the electrolyte. The role of electrolyte plays diluted sulfuric acid, and during the discharge process, the half reaction in this cell can be considered in two steps. The first one, oxidation of lead to plus cations at the anode, and the reduction of lead 4 oxide to lead 2 plus at the cathode. And the second step is precipitation of lead to sulfate at both electrodes. During charging, the opposite reaction occurs. When an automobile engine is started, the battery is first discharged. When the car is in motion, the battery is constantly recharged by an alternator powered by the engine. As the plates of the battery become coated with lead 2 sulfate and the electrolyte dilution exceeds a certain level, the battery must be recharged by connecting it to an external electric source and the reversed non-spontaneous reaction force. And this is the following reaction which must be forced. The standard voltage of the cell is 2.05 volt. We can see two anode plates are connected in the parallel fashion as two cathodes 1 are. The parallel connection increases the electrode area in contact with the electrolyte solution and increases the delivered capacity of the cells. In reality, 6 cells are then joined in a series fashion, plus 2 minus, to produce 12-volt battery. To reduce global greenhouse gas emissions, we need to shift toward a low carbon energy system. If we reduce the cost of renewable technologies such as solar and wind, we will make them cost competitive with fossil fuels. However, to make it happen, we still need low-cost energy storage, such as lithium-ion batteries. They are very important. I'd like to describe them more thoroughly. Lithium is the third lightest element and has one of the smallest ionic radii of any single charged ion. These features allow lithium-based batteries to have a high gravimetric and volumetric capacity and power density. Some definitions. Volumetric capacity was defined as a discharge capacity divided by the maximum thickness during cycling. So this is the energy density per unit volume. The gravimetric capacity, in turn, This is specific energy density. It's a measure of how much energy a battery contains in proportion to its weight, and the unit of it is watt-hours per kilogram. Watt-hours per kilogram. So energy density, specific energy density is equal to nominal battery voltage multiplied by battery capacity in ampere hours per weight per kilogram. Energy density is often confused with power density, so it is important to understand the difference between these two. The gravimetric capacity, the power density is the amount of power per unit volume or mass. So this is the time rate of energy transfer. This is power density. The difference between these two, I mean power density and energy density, is similar to that of energy and power. Batteries have higher energy density than capacitors, but capacitors has a higher power density than batteries. Thus, batteries may store more energy, but capacitors can give off energy more quickly. Each gram of lithium represents Faraday's constant divided by 6.941 or by 13,941 coulombs. At 3 volt, this gives 41.7 kilojoule per gram of lithium, or 11.6 kilowatts hour per kilogram of lithium. This is a bit less than the heat of combustion of gasoline, which is equal to 46 kilojoule per gram. Since 1991, the prices of lithium-ion batteries have fallen by around 97%. Prices fall by an average of 19% for every doubling of capacity. The fact that this rate of reduction doesn't appear to be slowing down is very promising. Electrical energy storage plays an increasingly important role in modern society, in our daily lives. A number of portable devices, as well as the development of electric vehicles and smart grid energy storage are highly dependent. They all are highly dependent on lithium-ion energy storage devices. The lithium-ion batteries exhibit high energy and power densities, long cycling life, and relatively low environmental impact compared to other rechargeable battery types. There is still a need for batteries with longer cycling lives and higher power and energy densities to power advanced communication facilities, plug-in hybrid electric vehicles and fully electric vehicles. The properties of the materials depend on the kinetics of lithium insertion and extraction. Lithium diffusivity benefits from high surface area and not too long diffusion path in the material particles. The mechanical stability and limited diffusion of soluble species are heavily dependent on factors such as particle size and spacing, pore size, and surface area. The materials of both anode and cathode are compounds containing lithium atoms. The positive electrode is composed of lithium intercalation material, generally a bulk crystalline metal oxide such as lithium cobalt oxide, and the negative electrode is composed of lithium host, traditionally graphitic carbon, which is electrically separated by a polymer membrane soaked with a lithium-ion conducting electrolyte. Liquid electrolytes in lithium-ion batteries consist of lithium salts, such as lithium hexafluorophosphate, lithium tetrafluoroborate, lithium perchlorate, lithium cobalt oxide, and so on. And in organic solvents such as ethylene carbonate, dimethyl carbonate, diethyl carbonate. During discharge, an oxidation half reaction at the anode produces positively charged lithium ions and electrons. Lithium leaves the negative electrode, anode, and is inserted to the positive electrodes. The oxidation half reaction may also produce uncharged material, which is unfavorable, that remains at the anode. Lithium ions first of all move through the electrolyte. Electrons move through the external circuit, and then they recombine at the cathode in a half reaction. During discharge, electrons flows from the negative electrode anode towards the positive electrode cathode through the external circuit. The reactions during discharge lower the chemical potential of the cell, so discharging transfers energy from the cell to wherever the electric current dissipates its energy. To summarize, during discharge, lithium ions carry the current within the battery from the negative to the positive electrode through the non-aqueous electrolyte and separator diaphragm. During charging, these reactions and transports go in opposite direction. Electrons move from the positive electrodes to the negative electrodes. In the reverse direction of a discharge current. The lithium ions then migrate from the positive to the negative electrode where they become embedded in the porous electrode material in the intercalation process. The intercalation process is the reversible inclusion or insertion of a molecule or ion into layered materials with layered structure. Examples are found in graphite. The structure of the guest host compound is only slightly perturbed from the host structure. The full reaction which proceed in lithium-ion batteries during discharging left to the right and during charging right to the left. This is the end of part 1 of this lecture. Thank you for your attention.